thank you for the invitation. Thank you all for being here attending my talk. I am, as you might have heard, Dr. Vincenzo De Maio from TU Wien. And in this talk, I'm going to show a bit my research work in the area and also how we can use cloud technologies to access quantum machine and actually use them for research and potentially for something useful in the future. First of all, why we are doing this? Why we people working in cloud computing should bother about quantum? The reason is this one. You might have seen this plot already. The Moore law. We see how the computational power grew in the last years and how this didn't scale with the demands of our current applications. And this is not for us. Nobody is to be blamed for this. We just couldn't predict it would come up this way. Just to make you understand, around this time, there was a guy called Bill Gates. You might have heard of him. He said something like 16 megabytes of RAM will be enough for everything. And a bit further in time, IBM said there will be a market in the world for maybe 5 computers. So it's something that we couldn't predict. Not even the best people working in the field could predict. And so demand continued to scale, hardware continued to grow, but at some point we reached a stagnation. From this point on, instead of having more and more, I don't know if you are old enough to remember, but there was a time where each 6 months you were getting the new Intel processor with more gigahertz, like a little bit more gigahertz, or like and at some point they started to stagnate. We started to have instead of having more powerful processor, to have just more processor in the same CPU. And still, we cannot cope with the increasing demand of current modern applications. And this is especially true with current machine learning application. To make things even worse, what about data? We have now smart devices. I guess any of you has a sort of smartwatch or even a mobile phone. And the amount of data that they produce is dramatically increasing year by year. And there are always more and more devices that produce data that have to be processed and stored. And this number is only expected to grow. And the question is, can current hardware deal with this? There are different solutions, but what research community is looking into is how we can consider alternative forms of computing, the so-called post-Moore computing. This is why I am here today. And our experience comes from this FFG project. It's a joint collaboration between IBM, JKU, MatTech, University of Innsbruck, and AQT. So you have Austrian startups working in quantum, and IBM, that is definitely not a startup, and and many players working in the field. And the idea was to develop a dedicated ecosystem featuring quantum and HPC nodes, and by means of cloud technology. It's an interdisciplinary collaboration. We have computer scientists, engineers, physicists, and I dare say one of the most interesting and life-changing experience because having to deal with different point of views of what is computing and how we see the same problems, it was something very interesting for us as a scientist. First of all, what is quantum computing? I will give a very brief overview to be sure we are on the same page. The idea is that it's based on principles of quantum mechanics. The idea is to exploit quantum effects. We want to exploit effects that are available in quantum computing, such as superposition and entanglement. I'm not going to explain them in this talk. It will take too much time. The idea is that we want to exploit them to achieve some theoretical speedups, because there are some proven theoretical speedups for very specific problems. And the idea is, can we use this speedup to improve our computation? Can we use them in some way to improve what we are currently doing? And however, what is the challenge of developing quantum applications? The Schrödinger cat is a metaphor of non-determinism. Like until we measure, what we have is a non-deterministic outcome. At the moment, each measurement can yield different result. Let's say we do our computation, and when we measure, it can collapse into different states. So there is an intrinsic non-determinism in our computation, and we need to deal with. The idea is that we run our computation several times, and the correct result should appear with higher probability. What is important? Okay, what is important also is to achieve, we need to use superposition and entanglement in order to make sense of it, because technically you could run all your computation, classical computation, in quantum. The point is, why would you do that? Like, which is non-deterministic, it's not giving you anything in addition. It makes sense only if you can exploit such effects in order to get a theoretical speedup, and you can use them in your computation. Actually, there is this theorem that says that you must exploit entanglement if you want to achieve any speedup. Now I will go through some, I will not give more technical details, but I will just give some ideas of just to be on the same page. How does a quantum computer look like? People from IBM will recognize this. This is one of the leading technologies. It's a superconducting machine. But you have so many others out there. Probably there is a new quantum machine coming up while I'm speaking to you. So you have D-Wave. This is not a universal quantum machine, but it's an analog, it's a type of machine, quantum machine that is specifically suited for optimization tasks. Then you have photonic quantum machines. Those are, even physicist friend says photons are weird. But still, you can guarantee. You can get very interesting result here. It's a very interesting computational model and can guarantee some speed up in some case. And then you have ion traps machine. This is, I took this picture myself in the University of Innsbruck, and it's very fancy. You have all these lasers and mirrors, and I'm very proud of this picture. I show it to all my friends. I don't have many friends, as you can imagine. So, one other thing is, also another thing, do I need a PhD in physics to work with quantum computers? No, it's an interdisciplinary field. You need to have some understanding of computing and to understand the quantum effects, but you don't need to know the physical detail of the machines you're working with. It helps, but you don't need to go that deep. Also, will quantum computers destroy the internet? How many times you heard this? The answer is, of course, no. Shor's algorithm is a potential threat, but there is already post-quantum cryptography at work. We are already talking today about post-quantum cryptography, and this is also, again, in that case also is probably not going to be the case for many long time. Is RSA dead because of quantum computer? Again, as a direct consequence, no. Because yes, Shor's algorithm can factorize a RSA key in polynomial time. Still, as far as I know, the biggest application was use the key with the was a 6-qubit key. So definitely not something that is relatable. And even if we would have tomorrow a machine capable of factorize 128-bit key, or even more, like I think now we have 2048, the easiest stuff would be, okay, we just double the key, and good luck then for the quantum machine to catch up with the current technology. So, will quantum computer replace all classical computers? Of course not. It is more likely that they will be used as accelerators. Like there will be some very specific computation that will be run on quantum machines, so similar to what happens with GPUs or with TPUs and FPGAs. Do I need to learn some esoteric programming language to work with quantum computers? Again, no. We have already libraries using Python for it, and then you have Q# and Silk, also just to make some example. Are quantum computers best used for large amount of data? It's a debated topic. Basically, there are some cases where it has been proven that you can represent the same data with less amount of qubits, but it's debatable what you can do with it, because also then you have to there are so many other factors to consider. And then, can we solve NP-complete problems by using in polynomial time with quantum computing? The answer is we don't know. Most probably we cannot. Because there are some specific studies where there are some specific cases, like in specific complexity classes, where quantum can actually help, but we don't really know exactly what this will mean for NP-complete problems. For sure, if this will happen, the computational hierarchy, the complexity hierarchy will collapse, but at the moment we don't know much about it. Now, what is the state of the art? We are now currently in the noisy intermediate scale quantum era. We have different, this is how programming works. We have a classical hardware that will prepare some state by doing some form of preprocessing. We are preparing something, the data that are, and the input will be prepared and put on a quantum machine into a format that the quantum machine can understand and process. We have from bit to qubit, just to simplify the problem at the extreme. Something will happen on the quantum machine, computation will happen, and then we measure and we obtain something out of it by applying some post-processing, like we will have some error correction and other different things that in order to make good use of this data. The problem that we need to solve are manifolds. Again, translate the classical input into a quantum state. Then we want to describe our computation in quantum into a high-level language, into something, and this has to be translated, like we want to use Python, Q#, whatever, and this should be translated into something that the quantum machine can understand. This is an example of how to describe your computation. This is a circuit model. There are other models of computation, but this is the most used one. And this has to be translated into something that the machine can understand. Then the N there, this stands for noisy. These machines are unstable, and there is error correction to be performed. To address this, there are also limited number of qubits available. The IBM Open Plan allows you to use up to 100 of qubits, but actually the overhead that you will get by managing such a volume of qubit, it will not make it pay off. So in the end, the qubit that you can use efficiently are in the order of a tenth or 20, depending on the application that you want to use. And also, the hardware deployment is non-trivial. As you can imagine, these kind of things cannot go under your desk. So you can, there will be different facilities to host this kind of computation. Actually, for this kind of machines, you need cooling up to millikelvin. There are other machines that can operate at room temperature, but still you need specific hardware for it, for the other thing. So definitely, it's not easy to deploy this hardware, and this is where actually cloud computing can help us. I mean, this is what cloud computing excels. We can access hardware that is hosted somewhere else, and we can use it and allocate and do stuff with it without worrying about the complexity. I mean, remember the picture of before, all this heterogeneity. We don't want to deal with the heterogeneity. We don't want to know if our machine is an ion trap, is a superconducting. I mean, we might want to know if we want to further improve our computation, but if we are simple users, we may not be willing to deal with the complexity. And this is where cloud comes in. First of all, let's see how an execution will work. As I say, we will have a hybrid execution. We have classical machines and quantum machines. This is what we are going to execute. We have our high-level execution code. And then we will have, in this code, we will have different parts. We will have quantum tasks and classical tasks. We will have different parts that can go on classical and part that can go on quantum. Then there will be a component that we define as the mapper. This will decide exactly where to allocate each task, because also the point is also to decide where to execute, because okay, quantum task can be executed on different quantum machines. There are different requirements and different topology, and this is where we use interface with the cloud to decide where to map. And then this comes from an hardware catalog, which is hosted remotely, and we can obtain information about the available hardware, and then we can perform our decision, whether we go on a CPU or a quantum processing unit. There are different problems that need to be addressed. For example, we have the circuit has to be, the high-level description of the circuit has to be adapted to the machine that we want to use. And this is part of the circuit decomposition problem. Once we have that, we have to decide how to map on which hardware and at which point to execute. And then also the interoperation, this is very important because the result of the classical computation may be used by the quantum computation and vice versa. You need to be able to find a level of interoperation between the two machines. And this is a non-trivial problem because also the rate at which data are generated on quantum machines is very different from the one you can generate on a HPC supercomputer. And this is something that you need to deal with in order to actually scale your computation. Also, how we can execute our computation. We will have this kind of we have different models. First is execution of a circuit. You will have the pre-processing on the CPU. Then the circuit will be allocated on the quantum machine, and then we obtain our result on the CPU. When do we want to? This typical application for this are problems of, for example, if we are scientists and we want to perform experiments on a specific quantum state, representing a problem that is interest for us. What we do, we just prepare it, and then we collect data on the quantum state in order to take information on the state. Or if you want to use it for sampling. Quantum is actually very efficient for sampling problems, but this requires another tool. Another thing is that, okay, as we saw, quantum needs repeated execution to deal with the non-determinism, right? So if you want to how do we understand that our computation actually is delivering a result that it has a meaning for us? It makes sense. The reason is by doing repeated execution and collecting the most frequent result. This is this will result in a repeated execution until a certain number of samples is performed. And then we will collect the frequency and the amount of time at which the computation is performed. And we will get the result and perform our statistical analysis on it. This is how quantum algorithms are usually executed. And there is another model that needs to be taken into account, the variational quantum algorithms. I will go very quick on this, don't worry. I mean, the idea is that we have our solution is represented by a quantum state that is parameterized. Don't bother about this symbol, just see this as a function on a parameter vector. Of course, it will be a unitary evolution of a quantum state, but we don't go there, don't worry. Like this is where this is basically what we have. And the idea is, okay, these machines have limited power, have a limited power at the moment. So the idea is to leverage the classical computer for something that we are very used at. We are very good at it. I mean, the idea is that we want to optimize this function, see it as a function, for this set of parameters. And the idea is to do the optimization classically. We want to use basically the best of quantum, like the sampling and the superposition and all the quantum effects. But on the same time, we want to use the classical computer to solve this as an optimization, to solve this optimization problem. We want to minimize this function, and hopefully the minimum value of this function will correspond to the solution of our problem. Why would you do this? Because, I mean, optimization is something that we are very good at classically. We are doing this since the very beginning of computer science. This is something that we know very well how to do it. And the reason is to take the best of both worlds. So the idea, we want to determine the optimal set of parameters by optimizing classically this function. This is basically, the function will be dependent on the quantum state and the vector that you use for it. And the idea is you perform different measurement, and you optimize classically this parameter vector until you reach the ground state, which is the minimum value of this function, which will correspond to the solution of your problem. This is interesting, but it has many problems on it. I mean, it has some problems which we are not going to discuss in this talk, but I mean, I'm very happy to talk about it. This is where my research is at the moment. Anyway, just know that there are several applications to this model. You have machine learning, for example, quantum machine learning is based on this principle, and many other mathematical applications and chemistry applications. I send you some references in case you want to look into. This means again that we need to account for another execution model. You have now into the loop, we have not only the multiple sampling, but also the interaction with the classical. And this is exactly well, this is one model that we need to take into account when we want to develop our application. And this application of the model is variational quantum algorithms. Now, let's see an example of a quantum cloud. This stuff are available already on the internet. You have basically the IBM quantum cloud. You see different machines that are available that you can use, literally like using any Amazon instance. Like you have your instance and you can allocate stuff on them. And speaking of Amazon, there is also, of course, an Amazon service for quantum machines. It's called Amazon Bracket. And this is for a specific type, different type of quantum machines. IBM, of course, allows you to use their machines. Amazon Bracket has different type of machines from different vendors. And then you have also other type of machines, like this is not only for big provider, but also providers such as Quandela. Quandela is a provider for quantum photonic machines. And this is an example. You have different. This is just to show you that you have many cloud providers that you can use to run your applications. But exactly which type of application can you run with it? You have different application at the moment that can be used. They have molecular dynamic application. I mean, this is something that is. Molecular dynamics computation are there since the very beginning of computer science. They are a very common case of HPC. And I don't know if you are old enough to remember this project, Folding Atom. The idea is that you want to measure this. The idea was to let the user from home to borrow their computational power in order to perform molecular dynamics calculation, in order to perform different simulations and obtain result from calculation by borrowing voluntarily their computational power. And the idea is that with the quantum is a good use case for this, because actually most of interaction between molecules are modeled by quantum mechanics. And the idea is exactly, you have also a proven speed up for different molecular dynamics problems. And this is a part where this is exactly one of the typical applications where quantum can give us a hand. This is an example of how this will work. Like you will have in local your identification of atom segments where you want to perform calculation on. Then you will do an interatomic distance calculation. There is a very efficient quantum algorithm for this, which is called the swap test. And the idea you want to do some test on quantum, and then you will calculate the ground states using the approach that I showed you before, using variational quantum algorithms. And then based on this, you will do some visualization. We have some work on it. Of course, I am shamelessly advertising my research, I know. So this is what we have been working on in a specific case. Then you have other type of application. As a direct consequence of molecular dynamics, what you have drug and material discovery. You have the idea of this drug discovery as you have to simulate different processing of multiple molecules and different folding patterns. And this is the use of quantum could speed up the development of drugs and vaccines. This is not me saying, but actually there is a collaboration. There is Roche. You might have heard about Roche. It's a pharma company, and they are investing a lot of money into finding how we can use quantum in order to speed up this process. And the ultimate goal is the reduction of laboratory experiment and also cost of research and human and animal testing. Also, I leave you some reference on it in case you are interested in it. And then finance. Finance is basically modeling of stochastic processes. And as I say, quantum is basically deals with the probability distribution and the stochastic process. It's very natural way to simulate stochastic process. And this is one of the applications where people are investigating it. You have financial instruments that can be described by a linear vector space. And the idea is to use quantum to perform a better simulation of this. And this is a partnership between IBM and JP Morgan Chase about using quantum to simulate the financial stock market prices. And there are some results where it proves that it works particularly well in predicting very specific patterns. Also, cyber information security. I already mentioned we have RSA and Shor's algorithm. This is definitely something where quantum can be used, and not only to break cryptography, but also to test the so-called post-quantum cryptography solution. Again, some reference in case you want to look into. And then quantum machine learning. This is where I am mostly working in at the moment. And you have this can guarantee different advantages. There is potentially a faster processing because there are some computation that can be speed up by using quantum. You can have better pattern recognition, again, for financial stock market, and this can be applied especially for machine learning. You can deal more easily with high-dimensional data. I mean, these, again, under many caveats. And then there is a way, this is what I mentioned about using less qubit to represent the same amount of data. So there is a chance to perform some data compression. This is, again, part of our work. The last one especially was accepted 2 weeks ago into iClear. And this is how it will work. You will have, in this case, you preprocess the data set on locally and then use the cloud to find, to minimize your, I mean, the training of the cost function is basically, like minimizing the distance between your hypothesis and your initial and the target value. So the idea is to use this loop in order to identify, in order to train your model, and the output will be in the end a machine learning model. So this is very cool, and you might have heard a lot of talk about quantum later, about how quantum is going to change our life and so on. This is part of, this is just some of the sentences that I selected on the internet. Now, how much of truth there is in it? At the moment, this is where we are. I mean, it's very cool, it's very interesting for a researcher, but I mean, there is clearly an issue with scalability. The current machine don't easily scale because as soon as you try to put more qubits, there is a overhead of error correction that needs to be addressed, and not only error correction, also data transformation and many other things. Then you have high costs. Again, millikelvin temperature cooling, not something easy to achieve. We don't. There is a okay. There is a timeline. Okay. No. I'm almost done. There is an uncertain timeline to discuss, like to finish. The idea is that we don't know when some development will be actually released, and there is a lot of discussion about it. Limited applications, as I say, it can be applied only on very specific cases, and this needs to be also considered. Then we have to deal with noise and error correction. There is the recent result of Google with the Google Willow, which is very fundamental, very important, but we are still very far from fault-tolerant quantum computing. And again, the imbalance in the data rate. This is what I mentioned in the beginning of this talk. And I will talk, and this is a quote that I particularly like from John Preskill, like when you say that we know how to get big quantum speedups for machine learning and optimization, promising them into an investor meeting is fundamentally dishonest. You may wonder then, okay, why we are here? Why are we hearing you talking? Because yes, all these things are true, and as a scientist, I cannot overlook them. Again, but still, there is big industry players into it. There is, like you have Microsoft investing into Microsoft, Google, you have IBM and Amazon investing into this technology. And you have growing industry players. You have Quantinum, but also the many startups, such as AQT. AQT is in Innsbruck and Matek is in Vienna. So even Austrian startups, so you might want to consider that in case for your future. And also governments involved. Not to forget the theoretical speedups. So there is something. Okay, at the moment probably there is not much that you can do with these machines. But I would either say maybe in the 50s you couldn't do much with the first calculator as well. So we are probably here in the same stage in terms of for what concerns quantum. So this has the power. What I say, just concluding my talk, we can revolutionize industry and make quantum computing available to business, researchers, and developers worldwide. We can have, for example, different providers for different tasks. For example, we could use photonics for specific tasks and other type of technologies for others. We can develop service-oriented hybrid architecture for different industry-oriented problems. And we have to consider also HPC integration. There is still a lot to be done. However, without considering all the issues that we have in this field that also needs to be addressed. And this ends my presentation. Thank you for attending, and I'm happy to take your questions, if any.